Okay.
Before I introduce tonight's speaker, I'd like to say a little bit about next month's speaker and the month after that and the month after that. As Rich mentioned, well, first, next month's speaker is also very exciting because it will probably be the chief scientist for the Double Asteroid Redirect Targeting Mission, the DART mission, where we actually impacted an asteroid and moved it. And I've been assured that either the chief researcher from that mission, whose name escapes me at the moment, will speak, or else one of the top people from the team will speak. And I think the name of the asteroid was Didymos, if I remember correctly. And their results were even more successful than they thought. So there may be hope for our species after all. Cross your fingers, folks. Then after that, in May will be our first in-person meeting, and our speaker will be, oh shoot, I can't remember her name right now. She's at San Francisco State, one of the world's great expert in globular clusters.
Adrian Cool.
And yeah, there you go, Andrea Cool. And she's going to be speaking in person. And then we're having a friend of Rich's the next month, whose last name is Link. Help me out, Rich. What's his name? Gary Link?
His last name is Link? No, his last name is Erskine.
Erskine, yeah.
He's spoken to us before. It's Dave Erskine. Yes.
Dave Erskine, and he'll be speaking about his really cool, it's a spectrographic device, Rich. I can't remember.
It's a mechanism of enhancing spectroscopy using a technique called EDI, and he's been checking in with us on this for several years, and he now has funding to actually put it to some good use.
Wonderful.
So he'll be talking about that.
And my wife met him on the trail when they were out hiking. So anyway, so tonight's speaker, forgive me, Rob, I'm going to read this. So is Rob Zellem, and Rob is with NASA's Jet Propulsion Laboratory, as his T-shirt attests to. He's not just some guy that we got to wear a JPL shirt. I want to assure you of that. And like many of us, he is very, very interested in exoplanets. Rob, are you old enough to remember when we only knew 9 planets or 8 planets, depending how you count?
Yeah, I am actually.
And it's amazing to think that we're now over 5,000 exoplanets, thanks to such wonderful missions as, there I go again, TESS, for example. How's that?
Yeah, Kepler and TESS.
I couldn't remember Kepler. I'm so excited about tonight's talk. Anyway, so he's going to discuss tonight current near future and near future ground and space-based missions such as NASA's Hubble, TESS, and of course, James Webb Space Telescope, which we're all extremely excited about, and which Rich got to see in person. I'm jealous of him. And Rob is also going to cover some near future missions such as the Nancy Grace Roman Space Telescope and its Coronagraph Instrument, which is something that many of us have fantasized about for many years, I want you to know. It's a great idea. And we're going to be able to actually do direct imaging of exoplanets, and this will help us discover life, perhaps, in other solar systems if we get our spectrographs working really well. Anyway, Rob's, of course, an exoplanet astronomer, and he is an interesting person because he likes to drink port. And anyone who likes to drink port is okay in my book. And he's the JPL commissioning lead of NESSE, which a lot of you have probably heard about, the new multi-object spectrograph at Palomar that's going to study many of these alien worlds that we're now discovering. And shoot, I could go on and read all of this. Okay, I'll tell you where he went to school. He went to Villanova University, where he got his BS in astronomy and astrophysics, minoring in physics, mathematics, and classics. Rob, I'm dying to ask you about the classics aspect of this, because I love classics as well. And I won't try my bad Latin on him. And then he went to University College London in England. This sounds really interesting, where he got his master's in science, MSc in space science. And then he went to one of our favorite schools in the universe, the Lunar Planetary Lab at the University of Arizona. Yay! Which is a great place. And when he's not observing exoplanets, he enjoys jazz, piano, cooking, and trying not to kill all his plants. Rob, at the end of the meeting, talked with my wife. She's great with plants. So without any further ado, Rob Zellem talking to us about really neat stuff. Go ahead, Rob. I'll let you go.
Thank you so much for that awesome introduction. Really appreciate it. Let me get this show on the road. So I'll start sharing. All right, you should be seeing the full version of my slides. So hi, everyone. Thank you so much for calling in tonight. Really, really appreciate it. So happy to talk with all of you. I'm in Southern California, and today, hopefully in Northern California, was the same. It was a gorgeous day out here. Really, really beautiful after all of this rain and such. So I'm a scientist at NASA's Jet Propulsion Laboratory, and today I'll be talking about exoplanets or finding life in the galaxy, because honestly, I'm a giant Star Wars nerd. I love Star Wars so much. I grew up on it. I want to ride the Millennium Falcon. But in order to ride the Millennium Falcon, I have to find out where it is first docked. So I work at NASA's Jet Propulsion Laboratory. Here's a picture of JPL, obviously taken thousands of years ago, back when Southern California had lots of water in its mountains and hills. There's my building right there. And at JPL, I get to study exoplanets. So I'm an exoplanet astronomer. Folks always ask me, were you always wanting to be an astronomer, or were you always wanting to be an astronaut? And, ever since I was a little kid, it's always been something I really wanted to do. I've always been interested in NASA and space. I had space wallpaper when I grew up as a kid. Here's little Rob meeting his hero, I guess, the astronaut. Unfortunately, I am deathly afraid of heights, so I am not an astronaut. I think I am what is the next best thing, which is an exoplanet astronomer. And let's break that out really quickly. Exoplanet, well, that means that's short for extrasolar planet. In astronomy, we come with very non-inventive names and are also making very short names because sometimes we can be lazy. So exoplanet is literally short for extrasolar planet, where extrasolar means anything beyond our own solar system. And planet, hopefully you all know what that is. Otherwise, you might be in the wrong club. So therefore, an exoplanet is any planet outside of our own solar system. Most exoplanets we know of today do orbit other stars, but that doesn't guarantee that they do. Some exoplanets might have formed around a star and might have been gravitationally kicked out of the orbit and might be sort of free floating and might be what's called a rogue planet today. And an astronomer, you folks probably all know what that is. That is someone who stares at their computer for way too long. So actually, folks think that I do a lot of observing, and I kind of do. I do a few nights of observing every single year, but honestly, my greatest tool in my arsenal is my laptop. And that's what I usually do most of my day-to-day on, is here in my home office, a former guest room, thanks to COVID, using this to sort of do all of my work. And I'll go to a telescope most of the days, mostly virtually, and I'll call in and do some observing. But most of my work, my day-to-day, is done on my laptop. So at JPL, what I'm doing as an exoplanet astronomer is ultimately, again, giant Star Wars nerd, is trying to answer that question: are we alone in the universe? I think this is really one of the largest and biggest questions we really have as a species. Is we know there's life here on Earth. Out of all the 8 planets in our solar system, there's only life here on Earth. But then when we go out into the night sky and look at the hundreds, if not thousands, or millions and billions of stars in the sky, it stands to reason that there's planets around those stars. And perhaps there also might be life on those planets as well. So the idea of life in our universe is actually not a new idea. It's been around for actually the last few hundreds of years. So for example, Giordano Bruno was a 16th century philosopher. He's that Emperor Palpatine looking dude there on the top right. He postulated the existence of other worlds with other life on it. And then Isaac Newton, the founder, obviously, of Fig Newtons, he wrote in his book in Principia, where he actually discussed his theory of gravity. He said, and if all the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, we have 8 planets, 8 because Pluto's not a planet. We have 8 planets here in our own solar system. And when we go out into the night sky and we look at all those stars in the sky, it stands to reason that those stars will also have planets. And perhaps some of those planets will also have life on their surface. And we now know hundreds of years later that these two dead dudes are absolutely correct. We have actually discovered over 5,000 planets to date. And as our technology gets better, as we know where to look, when to look, how to look, we actually are discovering more and more exoplanets, planets outside of our own solar system. We now know to date that actually there are as many planets as there are stars in our own galaxy, which is absolutely incredible. So with many, many planets, perhaps there are a few that might be harboring life. So we've been discovering more and more planets every single year. So how do we actually go from planet discovery to searching for life? Well, here's an actual 3-step method. For our search for life, we have to find an exoplanet. We have to determine if it could support life. And just because it could support life does not guarantee that it has life on its surface. We actually have to find life, if it exists, on its surface. So first, let's look at how we can find an exoplanet. Well, when we're looking for planets outside of our own solar system, it's actually very difficult because they're just so much dimmer than their own host star. And they're so very far away. The closest exoplanet to us is Proxima, and that's about 3 light years away or so. But most exoplanets are on the order of 50, 100 light years away, if not longer distances all the way from us. And the host star is so much brighter than the planet that it typically outshines its exoplanet. So we either need to block out the light from the host star so we can actually see the planet orbiting around it, or we need to use other methods, indirect methods, to infer the planet is orbiting around its host star. And thanks to this, we've actually figured out a variety of different methods to find exoplanets. But the 3 that I'll be focusing on tonight are the radial velocity, the transit, and the direct imaging methods. Radial velocity and the transit methods have arguably given us the most information that we know about exoplanets to date. And I'm working on a direct imaging mission, so I am legally obligated to talk to you about direct imaging, or else my bosses will get angry at me. So always good to keep your bosses happy and stay employed. All right, so let's look at the radial velocity method. So this is sometimes called the Doppler shift or the wobble method. So when you have a planet orbiting around a star, the star will actually cause the planet to orbit around it because of the star's gravity. But the planet will also induce its own gravitational tug on the planet as well, on the star as well. And the planet will actually cause the star to wobble back and forth. And we can actually measure the wobble of the host star and then deduce that a planet exists there. So when the host star is coming towards us, its light is compressed and it's blue shifted. And when the host star comes away from us, its light is extended, it's red shifted. And by looking at that blue shift and red shift, we can actually infer that a planet is there, causing the star to wobble back and forth. And current technology can actually get to about 10 centimeters a second. So that's roughly a brisk walk. And from this, we can start to actually begin to look for Earth-sized planets around sun-like stars. And the reason that this method is so important is because this allows us to directly measure the mass of the planet. The bigger the mass of the planet, the more wobble it will induce on its host star, because the planet will have a lot more gravitational interaction on its host star. The smaller the planet, the less gravity it has, the smaller the wobble. So we can actually weigh planets by looking at its radial velocity measurement. The other method I'll be talking about tonight is the transit method. So let's pretend we're looking at any random star in the sky. If we're lucky, that star will have a planet orbiting around us. And if we're even luckier, that planet will pass in front of its host star and block out the star's light. And this method is very powerful because it directly allows us to measure the radius of the planet relative to its star. The bigger the planet, the more light it blocks out, and the smaller the planet, the less light it blocks out. So we can actually directly measure the radius of the planet relative to its host star. At best, this dip in brightness is about 1%. But again, this gives us the planet to star radius ratio. Also, as I'll be talking about a little bit later, this allows us to study the planet's atmosphere. We can actually observe how the planet's atmosphere absorbs some of the star's light. And from that, we can actually infer the composition of the planet's atmosphere as well. And this method has been used very successfully to discover 3,000 of the currently known 5,000 exoplanets, thanks to missions like NASA's Kepler and TESS and ground-based observatories as well. Some advantages with the transit method is actually you can do this fairly cheaply. I saw a post on the internet a few years ago. Someone used a single DSLR camera on a relatively simple barn door tracker to actually observe a transit. In our own collaboration, we have folks that are using a 3-inch telescope to get actually science grade observations of these transits occurring. And also, very importantly, this gives us the planet's size. So we actually directly measure how big the planet is relative to its host star. However, there are some disadvantages. So for example, we could be biased towards large planets in short period orbits because bigger the planet, the bigger the signal. We could have false detections due to stellar variability or eclipsing binaries. And also we need that geometry. If the planet is orbiting perpendicular to our line of sight, the planet will never pass in front of its host star. It will never transit its star. It will miss some of those transits. But the transit method has been used very, very successfully by many ground and space-based missions. So for example, NASA's Kepler and NASA's TESS mission, with a transiting exoplanet survey satellite, have been discovering thousands of new exoplanets. Again, today we know of about 5,000. TESS, which launched a few years ago, is predicted to discover an additional 10,000 exoplanets. So TESS will potentially triple the number of exoplanets that we know of today. So you might be saying to yourself, already know 5,000, why do we care about an extra 10,000? And the reason is because we want to identify those planets that are most amenable for atmospheric characterization. Those planets that we can then go and follow up with larger telescopes such as Hubble, James Webb, and Ariel, the European Space Agency's mission that'll be dedicated to observing exoplanets. They'll be launching at the end of this decade. We need to have targets for these 3 and multiple more after them, platforms that'll be observing these transits. Hubble has been observing about 50 or so exoplanets and characterizing their atmospheres to figure out what their compositions are. James Webb has been observing a few handful of exoplanets, but likely at this clip, it'll be looking at tens, if not hundreds of exoplanets by the end of its lifetime. And with every single new observation, James Webb is revolutionizing the field of exoplanet spectroscopy and atmospheres. As I mentioned earlier, Ariel is a European Space Agency mission. This is a mission they'll be launching at the end of this decade. And Ariel is dedicated solely to looking at exoplanets. And it will look at hundreds, if not 1,000 exoplanets. And Ariel will basically give us the context for these James Webb observations. So Ariel will hopefully enrich the science returns that we're getting currently with James Webb today. And then I argue that beyond Ariel, beyond the 2029, 2030s, the next generation of missions will still be using the transit method to observe exoplanets and to determine the composition of their atmospheres and perhaps also look for biosignatures, signs of life. But in order to use any of these telescopes or any telescopes in general to observe a transit when the planet passes in front of the star and blocks up the star's light, we have to know very precisely when that transit will occur. So let's pretend I have a favorite exoplanet and I write a proposal and I send it off to James Webb and I say, hey, please give me this time on this telescope. I have to know very precisely when that transit will occur. If there's a 5-minute uncertainty of that transit, I can do one of two things. I can either build in an extra 5 minutes of observing, which ultimately is not a great use of these telescopes. About an hour of James Webb time is roughly worth $1 million. And everyone in astronomy wants to, rightly so, use James Webb and Hubble and all the large ground-based observatories to do their scientific research. The other option, though, is to do some pre-vetting, to do some pre-observations from the ground. And this is where small telescopes, I'm showing data here from a 6-inch telescope, but telescopes as small as 3 inches can actually help enable additional NASA science. These small telescopes can observe these transits ahead of time, refine their transit times, and then help us predict when the next transit time will happen more efficiently. And then as a result, we can then use James Webb, Hubble, any large ground-based telescope or space-based telescope in the future to then use that time more efficiently to observe and characterize their atmospheres. And that'll save time, that'll save money, and hopefully that'll expand their science capability. So sort of taking this into account, here's some actual transit data. This is of an exoplanet called HAPI-32b. This is a hot Jupiter, so a large Jupiter-sized planet orbiting very close to its star, so it's very, very hot. This is about a 2% transit signal or so. And despite this transit being around a relatively dim star, 11th magnitude, 2% signal, this is a 6-inch telescope. It didn't have perfect tracking. The target wandered by over 300 pixels across the focal plane. And there are no calibrations taken out of this data. We looked at data like this and we were just absolutely amazed and inspired by the precision that small ground-based telescopes could really achieve. So we started thinking, we have this problem of needing more efficient observations on large ground-based telescopes and space-based telescopes. We needed to update these timings. We also had 6-inch scopes that could directly do these observations for us. So that made us launch this this project called Exoplanet Watch, which is a citizen science project to monitor transiting exoplanets. Exoplanet Watch is a project that just launched officially this past January. And this is a campaign aimed at citizen scientists to routinely observe high priority transiting exoplanets to keep their mid-transit times and orbital periods precise. We're a collaborative effort to complement existing surveys. We have an open collaboration with ExoClock. We're members of TFOP, SG1, and the Single Transitors Group. All of our data is immediately public to the entire community. We have no proprietary phase. Our pipeline runs every other night, and you can grab the latest results from our pipeline off of our website right now. We also have an opportunity for community feedback and target requests. We have professional astronomers that come to us and say, hey, can you help us monitor this exoplanet? And we are more than happy to support that. But one thing I'm really excited and proud of is that observers will be listed as co-authors on any published results. If you do the work, you deserve the credit. So if your observations have been published for the first time in a peer-reviewed paper, you'll be invited as co-authors on that work. And we're funded through NASA's Universal Learning through the end of at least 2026, but hopefully many more years to come. So as a citizen science project, we have both science goals and education goals. The science goals I sort of went over, which is the efficient use of large telescopes. We can also search for new exoplanets. We can search for blended pairs. We can also monitor for stellar variability and confirm new exoplanets. But also our educational goals really at the end of the day are to inspire folks to perhaps join the field of exoplanets and astronomy, and to also engage the public in exoplanet citizen science and increase their confidence about their ability to do science. Well, let's pretend that I've inspired you to join our project. I'll step through really quickly. First off, what you do is you plan your own observations. This is if you have your own telescope. You can go on our own website and you can actually fill in your location on the Earth, and it will give you at least 10, if not 50 exoplanets that can be observed at any given night. Then you go out and you observe those exoplanets. But let's say you don't have your own telescope, or if you live in a location in the Earth that has cloudy skies or not great seeing, no worries. We have over 12 years of archival data that we are lending out to folks. So you can go onto our website, you can actually enter your email address and request some data from us and still fully participate in this project, even if you don't have your own telescope. Then, once you have data, either by observing it yourself or getting it from us, you analyze your own data. You can use whatever data analysis or data reduction tool you want. We have our own called Exotic that I'll be talking a little about later. Astro Image J is a super popular one that a lot of folks use, or you can use whatever you want. The only thing that matters is as long as it's in the correct format for uploading to the AAVSO's database, that's all that matters at the end of the day. We're really, really lucky that we have a great working relationship and collaboration with the American Association of Variable Star Observers, the AAVSO. They have their own exoplanet database, and they're letting us use it, and our users use it for free. And this is a huge contribution to the project, and we really, really appreciate it. So again, you observe your own exoplanet transit, or you get data from us for transit. You analyze it yourself, you upload it to the AAVSO's exoplanet database, and you sit back and relax. You all are mostly in Northern California. You have lots of great breweries up there, so maybe you'll open up a can of Anchor Steam, who knows, and you sit back, relax. You can get published as co-authors in some papers, or you can also go on our website and scrape some of our data products and publish your own scientific results as well. The only thing we ask is, again, if you're publishing data for the first time by an amateur astronomer, you invite them to be co-authors, and then you cite our paper, you give us an acknowledgement. Pretty easy, low bar of entry. What's happening on the back end, though, is we have this pipeline called Citizens. Citizens is an acronym that stands for the Citizen Initiated Transit Information Survey Enabling NASA Science. Kind of a mouthful, admittedly, but that's not a typo. It's purposely spelled that way. And what Citizens is, it's a fully automatic pipeline. It goes out, it scrapes all the latest data from the AAVSO's exoplanet database. It refits all of that data just in case some values might have changed over time. And then it immediately publishes all of those results to our website. So you can actually go right now on our website, just Google NASA Exoplanet Watch, and you can see our latest results. And hopefully they shouldn't be more than a day or two old. So we're always trying to be up to date as much as possible, and really showing all of our users' results as soon as they come in, as much as we can. So I talked a little bit earlier about Exotic. This is our exoplanet transit interpretation code. This was originally built in Python, which is a computing language, and you can run it with one of two ways. You can either run it locally in your own machine, but the way we recommend that folks run it is on the Google Colab Cloud. So basically what that enables you to do is if you have a free Google account, you can actually run Exotic fully on one of Google's remote servers. So you never have to download or install any software. You can actually use Google's servers to fully analyze all of your data for you. So you don't have to worry about installing pipelines or packages or code at all. You just run it locally or remotely in the cloud, and you can actually get from raw FITS files to a science grade light curve, such as this, in as little as 4 minutes. And I can say it's science grade because we've actually used Exotic to publish in our paper back in 2020. Another cool feature of Exotic is it has this real-time data analysis tool that allows you to actually reduce your data in real time. So let's pretend you're at a star party. You know, if you're observing an exoplanet, it's pretty boring. If you're observing a transit over the period of about 6 hours, and you're looking for a tiny dip on the order of about 1%. But you can use Exotic to do a quick analysis of your data in real time. So you can point to your computer monitor and you can point and tell a passing member of the general public that says, hey, we're actually observing an exoplanet hundreds of light years away from us, and it's blocking out its star's light and it's casting a shadow all the way to us, hundreds of light years away, casting that shadow here on the Earth. So if you're interested in getting involved in Exoplanet Watch, we'd love to have as many people as possible. You can contact us at that email address there, or you can go to our website. But the easiest way for me to remember personally is just to Google NASA Exoplanet Watch. And we really hope to see some of you folks there. All right, I'll get off my soapbox. I'll get back to our regularly scheduled programming. I talked about the radial velocity method that allows us to weigh exoplanets or determine how massive they are. I talked about the transit method that allows us to measure the size or the radius of these planets relative to their host star. The third method I'll be talking about tonight is what is called the direct imaging method. And as you can probably figure out from the name, this literally is taking photographs of exoplanets. We're very inventive with our names in astronomy out here. But as I talked about earlier, directly imaging an exoplanet is actually very, very difficult. And that's because the star outshines the light from the planet. Well, let's try to make things as easy as possible for us. Let's take a really large planet. Let's also take a young planet that still has a lot of residual heat from it formed. So it's still shining in the sky. So we have this big planet that's bright because it's still shining, and we put it around a sun-like star. Well, even at that level, that planet is 1,000,000 times fainter than its host star. That's like looking for the light of a firefly around a lighthouse on the other side of the country. Now, hot young planets is kind of cool, sure. What I'm really interested in personally is looking for Earth-like planets, planets that potentially could host life on them. So if we take that same Earth-like planet and put around our sun-like star, that planet is 10 billion times fainter than its own star. That's like looking for the light of one bioluminescent alga around that same lighthouse across the country. So how can we directly image these exoplanets? How do we measure these planets to determine if they have the right molecular composition to support life, or if they have the signatures that indicate life exists on their surface? Well, what we can do is we can actually build something that will block out the light from its host star and then enable us to actually see the light around the star and see a planet. So those of you who are lucky enough to see the total solar eclipse that happened a few years ago, you might remember when the moon passed in front of the sun, you can not only see the solar corona, We can also see some stars in the direct solar neighborhood as well. And that's because the moon blocked out a majority of the sun's light. Well, we can actually make something called a coronagraph to block out the light from that star and to allow us to directly image the exoplanets or any point sources orbiting around the star. So here is actually a really great description of what an exoplanet is.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
So I'll be talking to the Nancy Grace Roman Space Telescope a little bit later in this talk, but that's basically how coronagraphs work. Magic, right? There'll be a quiz on this later. Kidding. But basically what it does is it simulates a solar eclipse. And this is actually what the name coronagraph came from, is that astronomers got really impatient waiting for the next solar eclipse to happen to study a corona of our own sun. So they pull a little disk in front of the sun, they simulated a solar eclipse, and they're able to study the corona of our own sun. And today, hundreds of years later, we're basically using that same technology to now block out the light from the host star and to observe the planets orbiting around that star as well. So here what I'm showing is actually some data from a ground-based telescope taken over about 7 years. So at the center of this image, you'll notice here this black disk. That is the coronagraph on this telescope. This is taken from the Gemini telescope, about a 8-meter telescope. Some of the light from the star actually gets around the coronagraph's disk. That's just because light will bend around a corner because light behaves as a wave. So sometimes you'll get light bending around there and a coronagraph is not perfect. But what this enables you to do is block out the light from the host star. And you'll notice these 4 little point sources. And what these are is these are extrasolar planets orbiting around their star in real time. So what you're observing is an extrasolar solar system. We can actually observe these 4 planets orbiting around their star over about 7 years in real time, which is absolutely mind-blowing to me. I'll be talking about the direct imaging method a little bit later in my talk, but the direct imaging method will be used potentially in future missions to help us take snapshots of not only planets and solar systems like our own, but also then Earth-like planets, and might enable us to make that next leap in our understanding of the universe, to discover planets that could harbor life, and even planets that might actually do have life on their surface. All right, so now what? All right, so I've been talking about we discovered actually over 5,000 exoplanets to date, and exoplanet discovery, in the last 20 years has kind of become sort of passe. I remember when I was an undergrad, we got announcements every month or so, or every few months, the new exoplanet was discovered and it was big news. But today we now know that exoplanets are everywhere. There are at least as many exoplanets as there are stars in the sky. And the discovery of a new exoplanet is kind of boring, honestly. So how do we make that next leap from exoplanet discovery to maybe perhaps discovering that this planet might have the conditions conducive to supporting life? Or this planet actually might have life on its surface. How do we make that next leap to planet detection, to planet characterization? So for example, how can we figure out if a planet has an atmosphere? And if a planet does have an atmosphere, can we determine what sort of molecules are present in the atmosphere? Does it have methane? Does it have carbon dioxide? Does it have carbon monoxide? Does it have water? Does it have the molecules necessary to support life? And if it could support life, does that planet actually have life on its surface? Just because it has the right building blocks for life to form does not guarantee that that planet has life on its surface. But still, we have to make that next step. We have to go from planet discovery to identifying the planets that could have life on its surface and might have the right conditions necessary to support life. So that brings us to step 2, determine if a planet could support life on its surface. So when we think about, planets that are supporting life, we are admittedly applying a very biased view on the rest of the universe, a very human-centric view of the rest of the universe. When we look at our own solar system, we have the 8 planets here. As far as we know, life only exists here on the Earth. And therefore we think, hey, if life only exists here on the Earth in the solar system, then perhaps we need Earth-like conditions elsewhere out there in the universe. So perhaps we need planets that are Earth-like. And one of the biggest driving factors of this is using something called the habitable zone. This is the zone where liquid water can exist on a planet's surface. This is sometimes called also the Goldilocks zone. And the reason we care so much about this distance or this zone in the solar system is because life, as far as we know it, we're looking at the Earth, requires liquid water to survive. So if we look down on our own solar system, we look at the sun, Mercury and Venus are a little bit too close to the sun. They're too hot. Life can't exist. Mars, unfortunately, is a little bit too far away. The ice freezes, or the water freezes out, and we can't have life on its surface. And Earth, especially this winter here in the SoCal, gets tons of water, and life can exist on its surface. So we're admittedly, again, using a very biased metric in that life requires water to survive on the Earth and in our own solar system. And we're applying that metric to the entire universe. But the reason we're doing this is because, again, we know of over 5,000 exoplanets to date. And in order to observe all 5,000 requires an immense amount of resources to do so. So we're sort of narrowing our search here. We're looking at the entire 5,000 planet catalog. We're trying to downsample into the 10, 20, 30 exoplanets that are most conducive that we think, using our very human-centric, biased view of the universe, to then focus on in detail, to then characterize and determine if life exists on their surface. So again, the habitable zone. This is the area or the distance that life could perhaps exist on the surface of this planet. But that doesn't guarantee that that planet could have life or even water, for example. It could be Mercury, no water, or it could be Earth and tons of water, or it can even be a Venus that has immense greenhouse gases where all the water on its surface is boiled away into the atmosphere. So how do we make the next step from, sort of saying that we think water could exist on the surface to actually definitively saying that this planet has water, other molecules that life could survive on in its atmosphere as well? Well, we actually use something called Beer's law. So Beer's law is actually an extremely important method that we use to actually observe the rest of the universe. And we can actually do so and actually determine molecules and their composition of various planets or objects out there by looking at the light from these objects. So I found a really great definition of Beer's law. I'll hope to share it with all of you. That is studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. This is definitely a version that I held steadfast to in graduate school, but here is the real Beer's law. And what this really does is this describes the absorption and scattering of light out of a beam. So let's break this down. Let's pretend we have a light bulb right over here. And in between us, the observer, and that light bulb, we might have a box full of methane gas, for example. So we're looking at this light bulb through this box of methane gas. Now, on the other side of that box, where we are observing from, we would expect that that light would be attenuated a little bit because that light is being absorbed by the gas inside the box. And that actually behaves fairly simply according to this law right here. So what Beer's law allows us to do is if we observe how light is, so after it's been attenuated by some absorbing medium, and we compare it to what it should look like, we can actually use this equation to back out the composition of the absorbing medium. So we can compare what we observe to what we should observe, and we can actually back out the composition of the gas, the molecules that are absorbing the light from that gas or that light bulb. So let's extend this into an astronomical example. Let's say we're an astronomer, we're observing a yellow star. That yellow star emits yellow light, and we would see it as yellow light. But if we put in between us and that yellow star a cloud of gas and dust, like a nebula, that yellow light becomes reddened because that gas cloud is absorbing some of the star's light. And then what we can do is we observe what the object does look like. That star looks a little bit more red than it should, and compare it to what it should look like. It should look yellow. We can actually use Beer's law to determine the composition of the absorber. And then astronomers on the other side of that telescope can then say, hey, there's molecules in that cloud of gas and dust. So purely by looking at the light, we can actually determine and characterize the composition of many of these astronomical things out there in the universe. And this works for exoplanets as well. Let's pretend we're looking at a planet. Now, planets, just like our own Earth, they'll have a very hot, dense core that's emitting heat and light. And as that heat and light gets radiated outwards, it goes through layers of the atmosphere that are farther from the center core of the planet. These outer layers of the atmosphere are cooler, and they actually cool the heat that's being radiated out. So that yellow light is cooled down, and that yellow light finally emerges from the surface of the planet as red light. And then astronomers on the other side of that telescope can say, hey, using Beer's law, I can infer that this planet has methane on its surface. Similarly, in our own solar system, we have our yellow sun. It emits light, yellow light, that reflects off of the surface of planets like Jupiter. Jupiter, because it has methane and clouds in its own atmosphere, will then re-emit or reflect the light from our own sun, but reflected that looks reddened. And then astronomers on their side of that telescope will then look at it and say, hey, using Beer's law, we know that this planet has clouds on its surface. So again, Beer's law allows us to characterize a planet's composition by observing how it emits, absorbs, and reflects light. And this is extremely crucial and helpful because the nearest exoplanet to us at Proxima is about 3 light years away, or take thousands of years to get out there. So we can actually leverage Beer's law to characterize the atmospheres of these planets without even having to go there. So now that you're all pros on a exoplanet observing and using Beer's law, let's look at some actual data. Here we actually have about 7 exoplanets that have been directly imaged. And we've arranged them here on this axis. Here's 7 planets. And on this axis, the y-axis, sorry, we've arranged them from relatively cool to relatively hot at the top. And on this axis here, we have spread out the light using a prism, much like the Pink Floyd album cover, where you have the triangle prism, the white light comes in, the rainbow comes out. We've taken that light and spread it across all of its wavelengths to analyze each individual wavelength of light. And what this will enable us to do is we can use Beer's law to characterize the light from these exoplanets to then characterize their atmosphere, to look at their composition. So for example, at these wavelengths right here, these are the wavelengths where water molecules most efficiently absorb light. So if you see a bump and wiggle at these wavelengths, you can infer that that planet has water in its atmosphere. Similarly, if you see a bump and wiggle at these wavelengths, that means that that planet might have methane in its atmosphere. And also, if that planet shows a signature at this wavelength here, that planet might have carbon monoxide in its atmosphere. So this is data actually taken by a ground-based telescope. I believe this was taken by Gemini, one of the twin 8-meter telescopes. There's one in Mauna Kea. There's one, I believe, in Chile as well. And some of you might have been observing this and might have noticed that there's some gaps in the data. There's some blank spots. And really what's happening here is that our own Earth is getting in the way. The same molecules that we hope to observe on exoplanets also are here on the Earth. And typically these are water bands. And Earth has so much annoying molecules like water and oxygen that get in the way of our observations, and they make certain wavelengths inaccessible from here, from the ground. So if you can't observe them from the ground, what do? You go up into space. And this is why, one of the reasons why space-based observatories are so very important to astronomy. It allows us to go above the Earth's atmosphere to get outside of that absorbing features of the atmosphere, and allows us to access wavelengths that we could not normally access otherwise. So Hubble, for example, has been able to get above the Earth's atmosphere and has been able to search for water on many of these exoplanets. And this is why James Webb particularly is such a transformative, important mission. James Webb and its orbit is above the Earth's atmosphere. It's above the absorbing patterns and wavelengths of the Earth's atmosphere. It enables us to access wavelengths that we could not normally get access to here on the ground. And James Webb, with every single observation, is literally making transformative science every single new data set. James Webb, not only due to its wavelength capabilities, it actually has a larger wavelength capability and sensitivity than Hubble, but also it's roughly about 3 times the size of Hubble. Hubble's about 2.4 meters across, roughly about 6 feet. James Webb is roughly between 6 and 8 meters across, so about 20 feet across. James Webb, on the bottom of this, you might notice this purple part. That's actually its heat shield that blocks out the light from the sun, because heat radiates at infrared wavelengths, where James Webb also operates, and that can actually introduce noise to your own observations. And James Webb is absolutely massive. Hubble, for example, is roughly the size of a semi-tractor trailer. James Webb, this bottom heat shield is about the size of a tennis court. James Webb is so giant that it actually had to fold in on itself like origami to fit inside the nose cone fairing of its own rocket. And luckily, everything worked out. It had no failures. It's working perfectly. It's actually working better than anticipated. And James Webb is expected to observe perhaps 200, if not more, transiting exoplanets. Again, it'll look when the planet passes in front of the star, and the atmosphere of the planet will absorb some of the star's light. Then we can use Beer's law to determine what molecules exist in that planet's atmosphere. And James Webb is enabling us to do that at not only wavelengths we've never had access to, at least on the ground and in space, but also at unprecedented precision. Another mission that I actually work on here at JPL is something called the Nancy Grace Roman Space Telescope. Nancy Grace Roman, she was actually NASA's first chief astronomer. She's sometimes called the mother of the Hubble Space Telescope because she was one of the actual main proponents of the Hubble Space Telescope. So we actually have her to thank for Hubble. And in her honor, they've named this telescope after her. It's actually very similarly sized in terms of its primary mirror to the Hubble Space Telescope. It's also 2.5 meters. But Roman has such a higher F number, an F1, I believe, or F roughly around there, that it actually has a very large field of view. It has roughly 100 times the field of view of Hubble. So the way to think about it is Roman can do similar science to Hubble, but 100 times faster. And it'll use this to study astrophysics, dark energy, and exoplanets. But also it'll have an instrument on board called the Coronagraph, which will enable us to do direct imaging of exoplanets. And currently Roman is set to launch no later than May of 2027. So basically right around the corner. So direct imaging, just for a background, has been done very successfully and very extensively with large ground-based telescopes, typically 5-meter telescopes or larger, so like a Palomar or something larger than that. They've only been mostly operating, though, in the infrared, and they have, due to their optics on board, have only been able to observe targets very far from their host star relative to our own solar system. So they've been mostly sensitive to young planets that still have heat left over from their formation, that are glowing in the infrared, that are also very far from their host stars. Roman, however, will be operating at visible wavelengths and have the capability to sort of shift that barrier even further in. So we'll actually be able to observe Jupiter-like analog planets, planets that are like Jupiter's at Jupiter-like orbits, orbiting around the sun-like stars for the first time. You might be saying to yourself, well, Rob, why do we care about Jupiter-like planets? We care about life, we care about aliens. Well, it's because in order to get to where we want to go, small Earth-like planets orbiting around at Earth-like radii or distances around from their host star, we have to get from where we are, big planets, far from their star, to where we want to go, small planets that are dimmer, that are temperate, where life could exist closer to their star. And we need this stepping stone. We need to demonstrate that the technology that has worked so very well on the ground can also be directly applied to space-based observing. And Roman gives us that stepping stone to get us from where we are to where we want to be. And the lessons that we learn from the Roman Space Telescope will be directly applied to large next generation ground-based telescopes that will be deliberately designed to actually discover life on their surfaces. So you might be saying to yourself, Rob, you've convinced me, fine. Hubble is amazing, James Webb is amazing, I'm excited about Roman. Why even bother with ground-based telescopes? Well, that's because space-based telescopes, they're very limited in the sense there's really only 2 that are operating right now, Hubble and James Webb, that can characterize exoplanet atmospheres. And everyone in the field wants to use these two resources. They're very, very oversubscribed. It is extremely difficult to get time and very competitive to get time on these two telescopes. Also, they're limited in their wavelength space. You can't just launch a new instrument and slap it on the back of Hubble or James Webb and get it working up again. But ground-based telescopes allow us to basically plug in these gaps. There's numerous platforms across the entire globe. They have tons of instrumentation. If I make a new instrument, I can just drive out to that telescope and install it. But as I mentioned before, there are also cons with observing with ground-based telescopes. For example, it can't, look through those atmospheric passbands where the Earth's atmosphere is very much absorbing. And also you can have lots of systematic errors. Despite this, we're still pushing forward with ground-based telescopes. I'm actually, as in that awesome introduction at the beginning of my talk said, I am the commissioning lead at JPL for the NESI instrument, which is the New Mexico Exoplanet Spectroscopic Survey Instrument. That's an instrument that has been installed a few years ago here at Palomar Observatory. That is the 200-inch or 5-meter telescope out at Palomar Observatory, which is between LA and San Diego and Escondido. And this telescope was for about 50 years the world's largest optical observatory. It was commissioned in 1948. And, despite this telescope being built 50 years before the first discovery of an exoplanet, we've been able to put our instrument on the back end and help observe exoplanets 50, 60, 70 years after that telescope was first built. So let me show you a cool photo of Nessie. No, that's a mythical sea creature. Sorry about that. Here's an actual photo of Nessie in the clean room here at Palomar. Nessie is in blue right here on its handling cart. Here's some of its hardware. I'm doing some testing here in lab. So what Nessie does is Nessie's actually installed the prime focus of a telescope. So normally when you think of a telescope, you have a light coming in, hits the primary mirror, hits the secondary mirror, and is reflected at the back at the cast focus, the cast grain focus of where your instruments, your eyepieces, or your camera is installed. Nessie, however, is installed the prime focus. Actually, we flip out the secondary mirror, light hits the primary and is reflected directly into Nessie to maintain a wide field of view so we can look at simultaneously as many objects as possible. But given that Nessie has to go at the top of the telescope, we have to literally lift Nessie from the ground floor over this very historic telescope. So here's actually some photos of our first ever lift test. There's Michelle Creech-Ekman. She's a professor and doctor at New Mexico Tech University. She's the PI or the principal investigator of this instrument, and her team have built Nessie. I love her shirt. There's a little photo of Nessie. This is I Want to Believe. Here is my boss at JPL, Mark, ignoring me as usual. But here are some of this is our first ever lift test to make sure that we can lift Nessie and install it successfully at prime focus. Here I am praying that our insurance coverage has started. But we were successfully able to lift it 110 feet up in the air over this very historic telescope, 200 inches, 5 meters across, and get it successfully installed at prime focus. Here is Nessie installed. We're doing some testing with it. Here's my boss, Mark. He's smiling. Actually, he's laughing at me because, again, if you remember from the beginning of my talk, I am definitely afraid of heights, folks. But as the Nessie commissioning lead, I have the privilege of having to go up in the air and get Nessie hooked up. But the flip side is I got some really cool photos of it. So here's Nessie installed successfully in the prime focus gauge. And here's my feet. So it's kind of a selfie. It looks like a spacecraft, which is kind of cool. And we've been able to get amazing data with Nessie already, even though we're just still testing the instrument out. We're able to get within a factor of 2 of the precision of Hubble. So God forbid, if Hubble were to suddenly fail one day, we can still potentially do Hubble-like science with an instrument like Nessie. All right. So That's how we can find an exoplanet. We can use those various detection techniques. We can then use Beer's law to analyze the light reflected or emitted or absorbed by that exoplanet's atmosphere to then characterize the atmosphere of that planet and determine if that planet could support life. But just because a planet could support life, it might have oxygen or methane or carbon dioxide in its atmosphere does not guarantee that that planet does have life on its surface. So we have to take the third and final step. We have to find life. So how can we find life? How can we look at observations of a planet and say conclusively that that planet has life? Well, let's do a quick little thought experiment. Let's launch the spacecraft out into space, maybe like a Voyager to explore the outer solar system. But while it's cruising on out, let's have it turn back at the Earth and analyze the light absorbed and reflected and emitted by the Earth, and use Beer's law to look for evidence, for example, of oxygen that is produced by plants and algae, or look for liquid water on its surface, or perhaps even look for signs of biological activity like cow farts, like methane. Well, the sort of thing we always have to be careful about is that we have to rule out other explanations. Any of these three things can be produced on a planet abiotically without life. Most exoplanets we're looking at actually have water in their atmospheres because water is actually one of the most abundant molecules in the atmosphere. Many of them also have methane, but a lot of them are not, as far as we can tell, are not conducive to having the conditions necessary to support life. So we have to rule out other explanations. We have to find out ways to conclusively detect and determine if that planet has life on its surface or not. And this is actually one of the major sort of things that folks are researching today, is looking for what's called biosignatures, little signs or bumps and wiggles in those spectra in that information that we glean from the planet's atmosphere and its surface that indicate definitively that life exists on the surface of the planet. Or we can also do other things. So for example, we can actually send messages out to aliens. The Voyager 1 and 2, which are built here at JPL in Southern California. These are launched in the mid-70s. They did that grand tour of the solar system. They have 2 golden records on board that actually have sights and sounds of the Earth, from crashing waves to amazing photos to folks actually saying greetings in their own native tongue. And this record, what it has on its surface right here, this cover, is actually directions on how to build your phonograph to read from the record, how to actually interpret the signal, how to display the signal on your TV, and also where that record came from as well. Similarly, folks have done observations and experiments in the mid-70s as well to send out signals to aliens as well. So for example, Arecibo, before that unfortunately died a few years ago, this was the world's largest radio telescope in Puerto Rico. It was so large that it fit in between a valley between mountains. It sent out this message on the right-hand side to this globular cluster, M13, or the Hercules cluster. And here's the message here on the right-hand side of the screen. At the top in white, this is demonstrating that we know how to count. Down here in green is about different elements and molecules. Down here in blue and white is demonstrating to aliens, hey, we're kind of smart. We know about DNA. You can see that double helix feature. Here's a picture of a person. Here is where we live. There's the sun, Mercury, Venus, Earth elevated because that's where the signal came from. Mars, Jupiter, Saturn, Uranus, Neptune, and folks, this was in the mid-70s where they didn't know any better. They have Pluto on this map, but now today we know better. Pluto should not be on here because it's not a planet, it's a dwarf planet. And down here in purple is a side view of Arecibo. So what this map is literally saying is, hey, folks, here we are. We're humans. We think we're kind of smart. We know about numbers and molecules and DNA. Here's where we live. Please don't come and invade our planet. So clearly, we need to keep Jeff Goldblum cryogenically preserved forever to help ward off any alien invasion. So these are some ways that we've been looking for life by sending out messages to be proactive in our search for life. So you might be asking, these happened in the mid-70s, and we have all these amazing missions that are looking for planets, that are characterizing their atmospheres, that are discovering new molecules, that are challenging what we think about planets today. Where are we now? Well, unfortunately, despite what the History Channel and Ancient Aliens might tell you, we have yet to make any conclusive detection of extraterrestrial life. And you might be saying to yourself, well, why not? Rob, you told me that there are as many planets as there are stars in the sky. Planets are ubiquitous. Planets are everywhere. Why have we not discovered alien life out there? Well, perhaps maybe our technology isn't just good enough. It wasn't until the mid-90s where I would argue that we have perfected the use of digital cameras to discover exoplanets, that we had the technology necessary to actually discover planets around other stars. And perhaps our technology to discover life maybe just isn't there yet, and we just need some more time. Or maybe we just haven't found them yet. Maybe we've been searching on this part of the sky, and aliens have been talking to us or existing on this other part of the sky. Jill Tarter, who is actually the inspiration for Carl Sagan's book Contact, the movie Contact as well, she had a really great way of boiling it down. She said that if we took the entire universe and shrunk it into the size of the Earth's oceans, despite all we know and have explored and discovered and understand about the entire universe, we have still explored the equivalent of one glass of water's worth. So there is still a lot out there for us to explore, discover, and understand. Or perhaps maybe we aren't just all alone. Maybe life really is that rare. Maybe it only exists here on the Earth, and perhaps we are all out alone out there. Personally, I think that life does exist out there in the rest of the universe, and we just haven't had the technology to observe it yet. But the future is bright, and I really think that we'll potentially have the ability to answer this question within the next 10 or 20 years. We've had this amazing foundational technology given to us by ground-based observing that continues to push the boundaries and give us new scientific understandings of exoplanets. Hubble, Spitzer, Kepler, TESS have all been discovering or characterizing atmospheres of exoplanets and challenging what we think about planets in formation and their compositions as well. James Webb, literally with every single new observation, is giving us transformative science that is just changing the field as we speak every single day. Roman, when it starts observing direct imaging of exoplanets, will advance the technology to give us information on how to operate and design the next generation of missions. And these next generation of missions that I'll be launching in the 2030s or 2040s will explicitly be designed to observe Earth-like planets in Earth-like orbits around sun-like stars, and have the precision to look for biosignatures to potentially discover life. So perhaps in the next 10 or 20 years, we'll finally be able to answer that age-old question, are we alone in the universe? And with that, thank you so much for your time, for paying attention, and I'm happy to take any questions.
All right, thank you. Excellent talk.
Thank you, Rob.
Before we do questions, I need to share my screen really quick to show you and everybody else that it's definitely possible to get involved in some of this transit analysis. And a couple of years ago, a group of us from EAS, can you see my screen?
Yes, we can.
a group of us from EAS used Exotic to do some mid-transit time corrections and submitted them, and had a lot of fun learning how this is done. Struggled a little bit with Exotic, but got it to work and learned a lot in the process. So maybe this is something we should be doing more of. And I imagine the software is probably improved over the last couple of years, and I'm glad to hear you could also run a local copy if you want to. But yeah, here we go. There's about 7 or 8 of us who did this, and it was led by a high school student from Stanford Online High School named Sujay Nair, who we gave an award to for leading this effort. So anyway, thought I would share that.
Thank you, Rich. That is absolutely wonderful.
Questions. We have questions. Dave, I'm going to let you start. You had a series of questions that you put in the chat, but I'd rather you ask them live.
Okay.
If you're, 1 or 2 to start with, and then we'll move on to others.
Yes, I just have, I'm going to try to restrain myself. Actually, Rob, you answered some of the questions later on in your talk, so I won't ask all of them. I think one of the important questions that a lot of people who are out in the audience who are not as technologically sophisticated as Rich will ask is, what sort of instrumentation would have to be slapped onto our telescopes to be able to do this?
Yeah, so typically, so the smallest telescope we've had that's been able to make scientific grade observations, call them high precision observations, about a 3-inch telescope. Mm-hmm. Typically, you'll need some sort of tracking mount. An alt-as will work, but the tracking on an alt-as mount will typically, the target star you're trying to observe for about 4 to 6 hours. That's typically the transit length of an observation. That star will wander across the field of view.
You're talking about a barn door mount on an alt-azimuth?
Yeah. So what we recommend, honestly, is an equatorial mount. If you have an alt-az mount, though, just as a heads up, you can still use it. You just might have to nudge the star back into the center of the field of view so it doesn't wander off the edge of your pixel of your detector. And then you'll need like a digital camera. We use some ZWO cameras that only cost like $100 to $200. So you don't need a very expensive setup at all to actually make impactful transit observations at all.
Rich, actually, you were just telling us about a CWO camera, I think, that you're using. Is that not correct?
I'm using it right now. It's got me and the cat.
How fortuitous. You would almost think that we planned this or something. I assure our audience we did not. We're not that smart.
I didn't know. We're not, definitely not. It's all luck.
Yeah, it's all luck. It's all luck. Rob, also, I have to say, I was really intrigued by your last slide of all the different upcoming missions. And I was hoping you could tell us a little bit more about some of those. Some of them I know about, some of them I don't. One of them obviously is a free-floating occulting shade, I believe, the Starshade Rendezvous. Could you talk a little bit about that? And just a couple of, I can't expect you to talk about all of these, but just talk about a couple of those that are out in the far future, because those sound really exciting and make me want to take really good care of my health.
Yeah, so LUVOIR and HABEX and OST, the Origin Space Telescope, those were 3 of 4 mission designs that have been proposed to the field for where NASA should sort of focus its efforts for the next flagship mission. So the current flagship mission right now is James Webb. The next NASA flagship mission is Roman. And then after Roman, it's sort of up in the air. It seems the community sort of has agreed together that there should be a mission that has the capability, the sensitivity to observe, directly image Earth-like planets in Earth-like orbits around solar-like stars, and have the sensitivity to look for biosignatures that could indicate that life exists on the surface of those planets. These missions are still very, very much in the planning phase. If I were to throw money on something, I would assume that they would use technology that has been sort of indicated or lessons learned from the Nancy Grace Roman Space Telescope and CGI. And that would be a coronagraph. So it has that little disc that I showed in that video that passes in front of the star's light. It has that sort of donut ring as well to break down or block out the remainder of the star's light. It has deformable mirrors. Potentially, though, those next generation missions could also use something called Starshade. Starshade, I forget exactly how big it is. I think it might be in the order of a kilometer large in diameter. But basically, this acts as an external occulting disk. Much like the chronograph is internal to your spacecraft, this would be external to your spacecraft, and this would fly kilometers away from your spacecraft. So this potentially could help block out the light of your star even further and enable you to observe dimmer planets, Earth-like planets around that star as well.
Absolutely, like something out of science fiction. What is LUVOIR? Can you talk a little bit about that? Very briefly.
Yeah, so LUVOIR, HAVEX, and OST were 3 of 4 missions concepts that were submitted to NASA. LUVOIR was the, let's see, luminous UV optical infrared wavelength telescope that was, I forget exactly how large it was, but it was larger than James Webb. It had that honeycomb sort of segmented mirror design. It was much larger than James Webb. HAVEX was the Habitable World Explorer. That was a single mirror design that was about 4 meters, I believe, across. And Origin Space Telescope was more of an infrared telescope. But what will likely happen is sort of an amalgamation of all 3 telescopes will be adopted. And right now, there's literally, it's being planned right now on what the mirror size will be, what the mirror design will be segmented, will be a single piece mirror, will the secondary be on axis, will be off axis. And these are all trades that are happening literally right now. We just got the name of it. The working name is the Habitable Worlds Observatory, which is exciting for exoplanet scientists because it infers that we'll be looking at habitable worlds outside of our own solar system, and perhaps we'll be looking for biosignatures, indications that life exists on these planets.
And the launch for a mission like that would be what, approximately 10 years from now, 15, 20? What do you think?
2030s, 2040s. So
Okay.
Probably 10, 20 years from now.
Okay. I got to take really good care of my health.
Let me get
take away vitamins.
let me get to some of the other questions. You can unshare your screen there for a sec.
Sure.
All right. Frank asked, in your talking about oxygen proving, or maybe not proving, that there was life, what side of the question are you on? Do you believe that the presence of oxygen is more likely to be a sign of life, or is the preponderance of possible sources of oxygen that are chemical rather than biological outweigh, in your opinion, the prospects for oxygen indicating life?
Yeah, I'm very much the type of person that thinks that, with great claims comes, sort of great justification or great evidence. I like to see things fully sort of fleshed out and have as much evidence or explanation as much as possible. And what we're finding on exoplanets today, because water is one of the most abundant molecules in the entire universe, we're seeing that almost all these exoplanets likely have water in their atmospheres. But a lot of these planets are inhabitable, as far as we can tell, by looking at Earth life and Earth conditions. And these planets likely do not have the conditions necessary to support life on their surface. So, just because we might see oxygen on the surface of these planets, a lot of this oxygen could happen abiotically without life producing this oxygen. So people smarter than me, honestly, are trying to figure out what sort of molecules we need to see in concert, what sort of compositions and amounts of these molecules do we need to see taken all together to say what sort of percentage of certainty if that planet has life on its surface. So, for example, I could see us in 10 or 20 years from now, we might look at an Earth-like planet, and then we'll say, with this confidence, NASA thinks that life exists on this planet's surface. I don't really think, because I like to be more conservative as much as possible when I'm doing anything in science, and just to cover my butt as much as possible, to be blunt. I think that hopefully we'll be saying that, with 90 degree of certainty, with percentage of certainty, with 75% of certainty, we think that this planet could have life and it might show these signatures of life. Taking the next step and proving it is actually extremely difficult. And making the next step, I think, is a big question that folks on the ground today are investigating. Let's say, if you see these 3 or these 4 or these 10 molecules or these signatures in the planet's atmosphere, this guarantees that life exists on the surface of that planet. And that's one of the outstanding questions of our field today.
Thank you. Great answer. There was Frank also reminds us that there was a Saturday Night Live skit where the reply by the aliens to the golden records was "Send more Chuck Berry." I'd forgotten all about that one. All right. Tanvi asks, what are the assumptions for using the radial velocity method? What if there are multiple exoplanets in one system?
Yeah, that's a great question. So radial velocity method, again, what that does is that searches and observes the wobble of the host star to the gravitational interaction or tugging of the planet orbiting around it. So you're actually not observing the planet, you're observing the star being wobbled back and forth by the planet orbiting around it. And if there's multiple planets, well, let's just think about one planet alone. If there's one planet in that system, you'll sort of see this sinusoid shape, this periodic shape of the star wobbling back and forth due to that single planet. But if you add multiple planets to the mix, you'll not only get this sinusoid shape, you'll also get this sort of superposition of an additional higher order sinusoid shape. So instead of looking like this, you'll get something that looks like this due to that other planet added to the mix. And people have actually been able to observe with the radial velocity method these extrasolar solar systems and actually been able to discover multi-planet systems using the radial velocity method.
Got it. So they use that data is superimposed, and you can use a Fourier, I guess, to tease it apart, and or whatever other method you want to use. And that's I always wondered about that.
Yeah, you can bin the data together using like a periodogram or a Lomskargel. There's a variety of different methods to look at it and sort of figure out, the periodicities in the signal to then figure out the periods of the planets.
Very interesting. Dave asked a question, and I had the same question. What are blended pairs?
So blended pairs. So this is actually mostly important specifically for TESS. So TESS is that all sky mission that's looking at the entire sky to observe new and discover new exoplanets. And what TESS is doing is looking at a slice of the sky over the northern or the southern hemisphere. But in order to maximize the viewing angle of TESS, so it can observe as much of the sky as much as possible, TESS actually has very large pixels. So if you took a pixel and you project it on the sky, TESS's pixel would actually be very big compared to maybe your own digital camera on your own 6-inch telescope at home. So what can happen is, since that pixel is so big projected on the sky, you actually might have 2 stars within that single pixel instead of just one. And what that does is it actually dilutes your transit signal. So when you're observing a transit, you're always observing that planet relative to its star. So when the planet passes in front of the star, it blocks out the star's light. But if you're observing a transit and there's another star within that pixel, again, what it will do is it'll take that transit signal and it'll dilute it or make it a little bit shallower.
Sure.
So a planet that's actually a Jupiter size or a Uranus sized planet, you might think is an Earth sized planet. So you actually might discover the wrong size planet. So in order to figure out if it's a blended pair or not, if it's actually 2 stars instead of 1, you need additional follow-up observations from the ground. And this is where small ground-based telescopes, even as small as 6 inches or smaller, actually can come into play, because they're actually able to get a smaller pixel size or a higher spatial resolution than TESS. It's able to then break out those 2 stars from the one that TESS observes into 2 different stars, and then figure out the true size of that planet orbiting around that star.
Very interesting. All right.
I have another question. I'm
Go
sorry.
for it, Dave. No,
Yes.
please. While I search around
Is
for
there-
others.
Is there an optimal field of view for observing for amateurs to observe with?
Not necessarily. It kind of depends on your target, honestly. So typically for ground-based observing of a transiting exoplanet, you would like the target star and a nearby comp star. So your comparison star should ideally be as bright, if not brighter than your target star. Ideally also similar spectral type. But what that comp star allows us really to do at the end of the day is allows us to map out the systematic errors in our system and quickly divide them out from our target star. So for example, you might have a change in seeing, or the star might be rising and setting over the course of the night. So as it rises higher in the sky, it gets brighter. As it goes closer to the horizon, it gets dimmer. And you can divide out a lot of those shared systematics between your target star and your comp star just by dividing your target star by your comp star's light, your comparison star's light. So some exoplanets are very nice and well behaved and they have comp star nearby. Some might be more devoid of nearby comp stars, and that's where a larger field of view can be helpful. But honestly, I'm not a big fan of spending unnecessary money. So folks that are interested in observing transits, give it a shot. And see what
use what
happens.
you got.
Use what you got.
And related to that same question is, what's the typical subframe exposure time that people use in order to get a data point?
It varies, honestly. Some people will do like a few seconds. Some folks use a few minutes. Our general rule of thumb, though, is to expose so your target or your comparison star, whatever is brighter, fills your pixel wells to about 0.5% or 50%.
50%, yeah.
Yeah, that keeps you nicely within that linear regime. Don't worry about saturating. You can go a little bit higher if you want to, but that'll mostly, sort of define how long your exposures are.
Okay. Cool. Thank you. That's a very useful answer. All right. Dave, unless you have any more questions, I think.
I did have a couple. I'm sorry. I don't mean to monopolize the talk here. How big are those pistons in Roman? You were saying they were really tiny.
Yeah, I think they're about 1 millimeter apart from each other, and they're about 64 by 64.
Oh my God, how do you make something that small?
That's why they don't let me touch anything flight projects. So I'm only on the science side. They let engineers that can do that actually touch that sort of hardware. Yeah.
I'd heard about Nessie before, but I didn't realize that you guys were going to place it in the observer's cage of the 200-inch at Palomar. I seem to recall a picture of Edwin Hubble in that same location. I don't think he had his legendary pipe at that time, but you don't want to drop tobacco ash on top of the 200-inch mirror. But he was up there in the same location you were in, and
totally.
It looks scary to me. So I was impressed that with your fear of heights, what was it like up there?
Yeah, it's 110 feet up in the air, and folks used to, back when Palomar was first commissioned, folks usually sit in the prime focus cage and actually help do precision guiding.
Yeah, I remember.
Someone would actually literally wear a 1940s World War II bombardier jacket that was heated. They would actually plug it into an outlet to stay warm over the course of the night, and it would sit there and just manually nudge the star back into the center of the field of view. Yes. And instead of having a person up there, we have Nessie up there, and I'm luckily either here in my office or observing in a nice warm data room of Palomar. So I'm very spoiled by comparison, for sure.
That's when astrophotography was torture.
Yeah,
totally.
Natalie asked a question, and I got a partial answer for her as well. What level of education do you need in Python or another programming language to get involved with Exoplanet Watch? And, in our experience, when we used Exotic and all of those tools to reduce that data, we didn't need to know any Python. We didn't need to know any programming languages. We just needed to know how to work with the tools that Google was providing us. So if you're able to work your way around an Excel spreadsheet or something like that, you probably have the technical skill to work with these data sets. And
Yeah,
I
and
mean,
that's
would you
honest.
agree, Rob? I mean, it's
Yeah.
kind of like the heavy lifting and programming has been done by you guys already.
Yeah, I hopefully, honestly, you should need no programming experience, no background in Python at all. We've actually spent a lot of time and effort the last year or two on making our data analysis tool Exotic a lot more user friendly. So you can actually fully run this from honestly your smartphone. So everything runs in the Google Cloud. You don't have to install anything locally to your own machine. You don't have to worry about installing Python packages. Everything is done for you. And we also have helpful tutorials, and hopefully soon we'll have helpful videos as well. But also, if you run into any issues, if you have any questions, we have a Slack channel where you can join for free as well, where you can actually ask us questions in real time. I get all the Slack notifications to my phone. I'm usually the one that answers those messages. You can also email us, and we're happy to step you through and help you through. Lots of helpful, really nice people on there that can help you get along and figure out how to get the data reduction done. So zero Python, zero programming background knowledge required for sure.
That's good because I'm a terrible coder. Thank you.
Well, that's why I hire super smart people like interns to do the coding for me, because I'm also horrible too.
Good, good. That's reassuring. What is the wavelength range for Roman?
Yeah, Roman is primarily operating in the visible. Sorry, so
Oh, it's in the visible.
500 to 700 nanometers roughly is where Roman is operating for CGI, the chronograph.
Does it go? Okay, does it go into the infrared at all?
Kind of slightly, depending on how you define infrared. It goes into about long words of roughly 700 nanometers.
Okay,
so not too much.
Not really too much. Okay, thank you.
Yeah, and that's to help sort of advance the technology in the field. Typically, mostly ground-based observing for direct imaging is done in the infrared. So now we're trying to push it into the visible, where we can start looking at reflected light. And the reason we care about reflected light, as opposed to the infrared, where it's mostly emitted light from the planets, is because reflected light tells us a lot about the planets, specifically their cloud composition. One of the biggest outstanding questions in exoplanet science is we don't know what the clouds of these exoplanets is made of at all. And by observing in the visible, where these clouds most effectively reflect light, we perhaps can put some constraints on the cloud particle size, their composition, and therefore figure out what these clouds are made out of.
Wow, very exciting, very exciting.
All right.
I don't have any more questions from you. Maybe we should end the. Oh, one other thing I want to remind people is this program has been recorded. Has it not, Rich?
It has been recorded,
so that it will be available on our website. So if you want to go over some of these details again, if you'd like to help Rob out, Rob, I suspect you're going to have more than a few takers out in our audience tonight. So, Rob, thank you very much. That was a wonderful talk. Absolutely,
very good.
Thank you so much for having me.
Yeah, please, in about a week, this will be available on our YouTube channel, and send friends of yours our way if they have the equipment or the interest in participating in this kind of research.
Yeah, but even if you don't have your own telescope or live in cloudy conditions,
you can work with other data sets. Yeah, when we did it before, we used a data set from the SRO, the Sierra Observatory.
Nice.
Yeah, so we didn't even capture the data ourselves. We just picked up a data set for the exoplanet observations.
And our club does loaner telescopes too, if anybody wants to try one of those.
Awesome. Yeah, just Google NASA Exoplanet Watch, and we should hopefully be the first thing that pops right up in your search bar.
All right. Well, thanks, guys. And
thank you so much for having me.
We'll see you some other time.
Yeah, really appreciate it. Thanks again.
All right.
Have a good evening.
Thank you very much, Rob. Wonderful.
Right. Good night, everyone.
Good night.